Hello everybody, welcome to another video example. In this video example we are going to solve for the exact solution of an Euler-Bernoulli beam using the program Mathematica. So on the right here we see that the beam we're going to solve for is a nice simple scenario where we have a beam where both of the ends are fixed and it is subjected to a distributed load of Q. Now, we know that the governing behavior for this Euler-Bernoulli beam can be represented by the following differential equation, where EI multiplied by the fourth derivative of the deflection function is equal to that distributed load Q. So we're going to go through Mathematica and figure out how can we solve for that deflection function Y, and once we know that deflection function Y, what else can we solve for? So the first thing we're going to define is the parameters. So I'm just going to comment in here parameters, and we can just go through and list all the parameters that have to do with this equation. So if we were to look at the beam itself, we can see two obvious ones. The first one is the length of the beam. So I'm going to call the length of the beam L, and let's just say that the beam is 6 meters long. So to keep my units consistent, I'm going to put it into millimeters. So of course 6 meters, same thing as 6,000 millimeters. Now if we look at the beam, we also see that it is subjected to a distributed load Q. So I can go Q is equal to, and we can basically have whatever we want. So for fun, let's just have it as, let's say, negative 50 newtons per millimeter, which is the same as kilonewtons per millimeter. So notice that when we did our derivations for all those equations that we had Q going upwards. And since our Q in this case is going downwards, we have to include the negative sign to represent that. And what we'll do later on is we'll just keep it as positive, and we'll show you that it's actually very obvious to see the mistake you make if you keep it as positive rather than negative. All right, so if we were to look at the governing differential equation, we also see that we have an EI term. So the E part is the elastic modulus or the Young's modulus, and I is the moment of inertia. So what we'll do is we'll start off with E, and we can see that there's actually a problem. Notice when I type in variables before they were blue, this means that they are undefined and therefore a valid option for defining them as variables. So that fact that the L is blue, it's good. It means that I can define it as 6,000. Same with Q. Q is blue, which means I can define it as negative 50. E, however, by itself, it's black, meaning that it's already a previously defined function or variable in Mathematica. Therefore, I can't just go E, that'll create a problem. So what I have to do is I have to get creative. I have to think of another name for E. So what I typically do is I just go EM, elastic modulus, something like that. So we're going to have our elastic modulus, and let's say that it's equal to 20,000 GPa, which of course if I'm looking for MPa, or 20 GPa, but if I want MPa, that would simply be 20,000 MPa. So there's my elastic modulus, or my Young's modulus. And I also need the moment of inertia. So one of the things I could do is just specify the moment of inertia, but that's typically not how these questions work. Typically what will happen is on an assignment or something like that, what they'll do is they'll give you the beam dimensions. They'll give you the height of the beam and the thickness of the beam. So what we'll do is we'll find the height of the beam as h, and let's say that the beam is 800 millimeters tall, and the thickness, or the thickness into the screen, or that E3 direction, that'll be the base, which is, I just put B, and let's say that that is equal to 500 millimeters. All right, so here's all our variables, and these are all the variables you guys need to solve for this beam. Now, I'm going to make my life a little bit easier because we know from the equation that we need the moment of inertia. So real quick, I'm just going to define the moment of inertia. And again, since we know that it's black, we can't just use I by itself. We have to add another letter or number, something like that, to distinguish it. So I'm going to go IG. IG is now blue, so that's good to go. And I know that my moment of inertia for a rectangular cross-section is just going to be base times height cubed. So I'm going to put in brackets height cubed, and all of this is going to be divided by 12. So this is my moment of inertia for a rectangular cross-section. If you guys are given a different cross-section, of course you guys can vary the moment of inertia accordingly. And just to make my life even easier, if we look at our equation, it's EI. EI is always together, so what I'm going to do is I'm just going to actually define EI as simply the Young's modulus multiplied by the moment of inertia. All right, and at this point, I'm good to go. I have all the variables I need for my equations defined. We can move on to the next step. Now, when we're dealing with Euler-Bernoulli beams, because of all the assumptions we made, we get a very nice differential equation, as you guys can see. Therefore, it's actually very easy to solve this differential equation, especially in Mathematica. So I'm going to create a new section right here, and I'm just going to call it differential equation, if I can spell, of course. Differential equation. In this section, we're going to solve this differential equation. Now, of course, with computer programs, there are many different ways you guys can tackle a problem. So if you guys already have a way to solve a differential equation, of course, it's perfectly valid. I'm not saying it's wrong. I'm just going to show you guys my personal way. So the first thing I'm going to do is I'm going to define my differential equation, and I'm going to move the parameters so that I have an equation that's equal to 0. So I'm going to go dE, which is my differential equation, and we know that it's EI multiplied by the fourth derivative of the deflection function. So EI, we've already defined above, so we're good to go, and we're going to multiply this by our deflection function. So you can call the deflection function whatever you want. I'm going to keep it simple and just keep it as y, and we have to keep in mind that we're multiplying it by the fourth derivative of this function. How do we do that? Well, we represent a derivative by primes. So this is the first derivative, the second derivative, third and fourth, etc. So if you guys want the fifth or sixth derivative, just keep adding primes. You guys can do it as much as you want. But we also have to specify what y is a function of. Well, of course, y we know is a function of x1. You guys can put it as small x, so if you guys want to, you guys can just do that. Perfectly fine. But I like to go uppercase big X or x2, whatever I want, really. It's completely up to you guys. That's more of a matter of personal choice. Now, another thing I said with this differential equation is I want to define it in terms of 0. So I have the whole differential in kind of one side. So if I move q to the other side, I get EI multiplied by the fourth derivative of a deflection function minus q. Now, of course, all of this here, that's going to be equal to 0, and you guys will see where that comes into play. Now, if you guys look at how we solve it, you don't have to make it equal to 0. Again, that's just a personal preference of mine. You guys can do whatever you guys find the most comfortable, if you will. All right, so now that we've defined our differential equation, we can solve it very easily. Mathematica is very nice in that it provides us with a function that solves differential equations. So what I'm going to do is I'm going to go sol, which is basically the solution to this differential equation. It's going to be equal to, and this is where I call that differential equation solving function. So that function that I told you about, it's called dsolve. So capital D, capital S, O-L-V-E, dsolve. Now, we can tell it's a valid function because it turned black. Again, if something's already defined in Mathematica, it will turn black. And if we're dealing with a Mathematica function, it'll always have square brackets around it. So this will be the function in itself. And inside of this function where we have that little red arrow, that's where we input our arguments. So the dsolve function actually takes in 3 arguments. And each argument is separated by a comma. So if we have 3 arguments, we need 2 commas to separate the 3. So I'm going to go comma, comma. And from here, I'm going to say, this is going to be the first input argument I need, my second input argument, and then my third input argument. All right, so we're going to have to deal with 3 different things, although 2 of them are actually very simple. The middle one, the middle argument, it's saying, what are you trying to solve for? What equation are you trying to solve for? Well, we already know that we're trying to solve for our deflection function, which is y, and it's a function of x1. So in the second argument, I'm going to go y of x1, and then the last one, it's asking what variable are we differentiating to, stuff like that. So we're just going to put x1 right here. All right, so the second and the third argument, very easy. It's just going to be your function that you're trying to solve for, and then the variable in that function. Nice and easy. It's the first argument where we put in the equations that we're trying to solve. All right, and this is why I've defined the differential equation above, because it makes it very easy. So the equation I'm trying to solve, well, I want to solve my differential equation when it's equal to 0. And this is why I made it equal to 0. If I wanted to, I could have made it equal to q and then removed the 0 above. Again, perfectly valid. That's the nice thing about coding. You can do whatever you want. But since I moved the q to the other side, I'm going to make this differential equation equal to 0. So all this is doing is it's saying, all right, here's your differential equation. Here's what I'm trying to solve for, and here's the variable. So what this function is going to do is try and solve this equation. Now, notice that when I inputted the equation, I just didn't put 1 equal sign. I have 2 equal signs there. So when you're doing logical things like that, it's actually going to require 2 equal signs. So if you guys put 1 equal sign, you guys will get an error. And I guarantee I'll be seeing a lot of that. All right, so at this point, I'm going to run the code and see what it gives me. So to run a code in Mathematica, you hold down Shift and then you press Enter. So from here, it says that my equation, y of x1, is equal to x1 to the 4th divided by a big number, plus, wait, what is this? C1. Oh, wait, I got a C2, I got a C3, and I got a C4. What is that? Well, keep in mind that when we're solving these differential equations, we're basically integrating. And once we integrate, we have a constant. So that's what these are. These are the constants. How do we deal with the constants? We utilize the boundary conditions of the beam. So if we look at the beam, it's very important to note the end conditions. In this particular example, the beam is fixed on both ends. However, we can change that. You guys can have a cantilever beam, which is fixed on one end, free at the other, or a simply supported beam where both of the ends are pinned. So this is where those boundary conditions are going to come into play. Now for our particular beam where it's fixed at both ends, that means that the deflection at both ends must be equal to 0, as well as the rotation at both ends are going to be equal to 0. So you guys are all masters of these boundary conditions, but the question becomes, how do I implement them into Mathematica so that I can easily solve for these C coefficients? Well, it's actually very simple. When we go back to our dsolve function here, all of the boundary conditions are actually going to be inputted into this first argument here. So if we're ever inputting multiple arguments, we have to do these little squiggle brackets. So instead of just DE is equal to 0, comma, I put in squiggle brackets DE is equal to 0, and because of that, I'm able to add additional arguments. So I can go DE is equal to 0, so that's my differential equation is equal to 0, but then I can go comma, and I can add in my boundary conditions. So again, one of the first ones is that the deflection at both ends of this beam must be equal to 0. So I can go y when x1 is equal to 0, well, we know this is going to be equal to 0. And same thing at the other end. So if I want to add an additional argument, I simply go comma, and then I can go y when x1 is equal to L, well, this is also going to be equal to 0. So again, don't forget the double equal sign. If you guys forget one of those, it's going to lead to an error, which sucks. No one wants an error. So I just added 2. We know that we have 4, but I just added 2, so let's see what happens. I'm going to go Shift Enter, and as we can see, we've eliminated 2 of those constants. We're only left with C2 as well as C3. So notice that C1 and C4 have both now disappeared. So by you guys can kind of guess, once we input those additional 2 boundary conditions, we should be able to solve for C2 as well as C3. So again, with this particular case, and remember, the boundary conditions are going to be important in this particular section. So for us, in this particular case, where it's fixed, we know that the rotation is also 0 at both ends. So I can go comma to add an additional argument, and I know that y prime, which is the rotation, when x1 is equal to 0, well, that's going to be equal to 0. And similarly, y prime, when x1 is equal to L, so at the other end of the beam, so the rotation there, I know that that's going to be equal to 0. So basically what I did in the first argument is I defined my differential equation, and then I defined 4 boundary conditions associated with that differential equation. So when I solve that now, I get my deflection function, and it's simply just a function of x1. So I got x1, x1, x1. The rest are just numbers. By this stage, I am actually good to go. All right, so what I'm going to do is I'm going to suppress this, and now we're going to look at something kind of funny. So when I go sol, which was the solution to that differential equation, and I were to run it, I get this right here. Notice that it's not just the equation by itself. What this solution is, or this variable, it says that y1 is equal to this. It's not just this itself, so it makes it kind of tricky. So what we need to do is we need to define the deflection function. So I'm going to create a new section, and I'm just going to call this deflection, whatever that is, deflection function. All right, so what I want to do is I want to take this right here, just the differential equation solution, this right here, and store that by itself as a variable. How do we do this? Well, I'm going to go y, which is going to be my deflection function, is equal to y of x1 when solution of 1. Basically, y is equal to y of x1 when, and then down here, x1 approaches this value. All right, so it's kind of hard to picture, but this is how you do it. I recommend just sounding it out. Again, y is equal to y of x1, this right here, when y of x1 approaches this. So if I were to do that now and run it, I get just this right here, which is my nice equation. So that's going to be my deflection function right there. So I'm going to suppress that. I'm going to come down here. because as we said in the theory, once we have that deflection function, a lot of possibilities open up. The first thing that we can do is we can solve for the bending moment as well as the shear functions. So what I'm going to do is I'm going to go shear and bending moment. Nice, easy functions to solve for, because we said that the moment is equal to EI times the second derivative of the deflection function. And we now have that deflection function. So what we can do is we can go moment is equal to EI times, and again, the second derivative of that deflection function. So the question becomes, how do I take a derivative in Mathematica? Well, again, it's really simple. There's a built-in function for that. That built-in function is simply d. Nice and easy. Everyone thought it might be derivative or something a little bit more crazy, but no, it's simply d. And we can see that because it's already blacked out, which means it's already defined. Now again, when we're dealing with Mathematica functions, they always have the square brackets around them for the input arguments. And for the derivative here, which is the d function, it takes in 2 arguments. So I only need 1 comma. Right here, I'm going to have my first argument. And right here, I'm going to have my second argument. And this is even easier than the dsolve function. So the first argument is, what equation do you want to take the derivative of? Well, I know I want to take the derivative of my deflection function. So all I need in the first argument is simply my deflection function, y. Nice and easy. The second argument is, what variable do you want to differentiate with respect to? Well, of course, my deflection function is just a function of x1. So this is where I would put x1 right here. Now here's the problem. This by itself, if I were to leave it like this, it's only going to take the derivative once. Now if we look at the equation, we know that it's EI times the second derivative. So I need to take that derivative twice. So how do we add in the number of times that we want to take the derivative? Well, we add in the squiggle brackets around the second argument. So just like before, how we're adding multiple inputs to a single argument, we say we want to take the derivative with respect to x1, and then you go comma, and I want to take it twice. All right, so what we do is in the second argument, we put what variable we want to take it with respect to, and we go comma, and then how many times we want to take that derivative. So if I were to run this and go shift enter, I now have my bending moment function, which as we can see here is going to be a quadratic function. Now using the same methodology, we can also solve for the shear function, which I'm going to call v. So v we know is equal to EI multiplied by the third derivative of the deflection function. So again, derivative, I'm going to use the d function. The first argument, what is the function you want to take the derivative of? Well, that's our deflection function. The second argument, we're going to put squiggle brackets. The first part, what is the variable? Well, that's x1. How many times do you want to take it? Well, we want to take it 3 times in this particular case. So if I were to run this now, I now have my shear function, which is just a linear in order. All right, so at this point, we solved for the moment, and we also solved for our shear function. So we're looking pretty good. Now this is great because then we can move on to the third step that we discussed in the theory, which is finding stress components. So again, we can use the shear and bending moment functions to then find stress components. So I'm going to come down here, add a new section, and we'll just call this stress components. I'm going to spell something wrong and you guys will all laugh at me, but I don't care as long as you guys are learning something. So there's 2 stress components that we can solve for. Remember, Euler-Bernoulli beams have 2 different stress components. The first one is the normal stress, sigma 1,1, and the second one is the shear stress, sigma 1,2. So we're going to solve for S11 first, and it's a nice simple formula as you guys can see. It's just -1 times the moment times x2 divided by the moment of inertia. Well, we have all those parameters already defined. So we got negative moment, again, the moment function we defined above, so we're good to go, times x2, and x2 is just a variable, so we just leave it as x2, and divided by the moment of inertia, which we defined as ig above right here. So that's it. If I were to go shift enter, I have my function for my sigma 1,1 component. Now notice that it is a function of both x1 as well as x2. So when it comes to plotting sigma 1,1, we actually have to play around with it a little bit to actually show what it means graphically. All right, so that's sigma 1,1. We also have sigma 1,2, the stress component 1,2, or the shear stress. And again, we have a nice easy formula where it's equal to negative v, where v is the shear stress, which we defined above, times by q, which we actually haven't defined yet, and that's evident by q being blue. Remember, if something is blue, it means it hasn't been defined yet. And then this is divided by IG, the moment of inertia, times B, which is the thickness of the beam into that E3 direction. So if we were to run this right now, we actually have a little bit of a problem in the fact that we have it in terms of Q, and we haven't defined what Q actually is. However, if you guys remember in the notes, we actually had a nice formula for Q, where Q is equal to B times, and then we have basically two sets of brackets. So it's times by something in bracket 1 and times by something in bracket 2. Now, the first part in bracket 1 is simply going to be the height of the beam divided by 2 minus x2. And then in the second bracket, we have the height of we have x2 divided by 2 plus the height of the beam divided by 4. So even though it looks really bad looking at the Mathematica code equation for it, it's much easier to see if we just look at the actual equation that, of course, is on the screen right now. So now that we have Q defined, I can suppress it, and if I were to run it, we now have a function for our shear stress component sigma 1, 2, and just like the stress component sigma 1, 1, it's a function of x1 as well as x2. All right, so these are how we get all the expressions for the deflection, the shear, the bending moment, sigma 1, 1, as well as sigma 2, 2. But now the question is, what does this look like? What does this represent? So what we're going to do now is we're actually going to plot the functions. So I'm going to go plot functions, just like this. And we're just going to go through the list. So the first one is the deflection function. Now the deflection function is just a function of x1. Therefore, we can show this or represent it by just a nice little single graph. How do we do that? Well, Mathematica has a function called plot. Again, since it went black, we know it's a defined function. And since it's a function, it's going to have those square brackets around it, just like this. Where inside of the square brackets, that's where we have all of our inputs. And I'm just going to scroll down a little bit here, and this plot function is actually just going to take in two basic inputs. All right, it's actually nice and easy. The first one over here on the left side of the comma, what function do you want to plot? Well, I want to plot my deflection function. So up here, I see my deflection function is stored as y, so I'm just going to go y. The second one is going to take in multiple inputs, so we're going to use our squiggle brackets because we're defining multiple things in that second argument. But even though it sounds scary, multiple things, it's actually really easy. So the first thing we want to define is what is the variable that we're plotting over? Well, we know we're plotting over x1. All right, nice and easy. The second one is, what is the lower bound? Well, we know we want to go from x1 is equal to 0. And then, of course, the third one is going to be the upper bound, where we want to go x1 is equal to 0 all the way to x1 is equal to L, just like that. So if I were to go Shift Enter, I can see my deflection function. Now, Mathematica by default will always give you an aspect ratio of 1, which is why this looks funny, even though the beam we know is much longer than the deflection is. So what we can do, or what I like to do to make this look more like a beam, is I like to add a third argument. So I add an additional comma. And what I like to do is I like to modify the aspect ratio. So see how aspect ratio pops up right here? What I can do to save myself some time, rather than typing it all out, is I can just go Tab, and it'll automatically fill in aspect ratio. And then what I like to do is I like to set it to 1/4. Now, if I were to run this now, as we can see, the graph looks much more like a beam would be, even though, of course, it's horribly to scale, something just like that. But you guys can see now what the deflection function looks like over the length of the beam. Now, taking this exact same plot, what we can do is we can copy it, and I'm just going to go down, and I'm going to paste it twice, because just like the deflection function, both the moment and the shear functions are just a function of x1. So once I've defined this plot function once, and I want to do the same thing for the moment and the shear, I can just go moment, and then down here, I can just go shear, because they are both being plotted over x1 from 0 all the way until L. So if I were to run this now, I can see that I have my deflection function, I now have my moment function, and then I also have my shear function. Now, if you guys are looking at these values, you guys are saying, whoa, those are huge. And although that sounds crazy, it makes sense, because if we kept everything in millimeters as well as newtons and MPa, then all the results are going to be newtons, millimeters, and MPa. So if we were to look here, this deflection in millimeters, that makes sense. 0.4 millimeters of deflection, that's very low, but of course we expected it under such little load. However, the moment, although it looks high, this is in newtons times millimeters. So if I wanted kilonewtons per meter, what I can do here is I can just go my moment function, and then I can divide it by 1,000,000 to give me kilonewtons per meter. And same thing with shear. Right here, shear is in the form of newtons. If I wanted kilonewtons, I can just divide by 1,000. So if I were to add those in and run it, I can see that the axes change accordingly. It's looking really good. Now let's also say that, hey, I don't know which function is which. I just want to add a little indicator above each. Well, it's actually pretty easy. So before we plot the function, we can use the print command. So just print, and again, it's a function, so it's the square brackets. And all you need to do is just do the quotation and put in what you want. So the first one we're going to have is the deflection function. So something just like that. I'm going to just copy this to save us a little bit of time here. Go enter and then Control V. I forgot what paste was for a second. The second one we know is our moment function. And then finally, the third one is our shear function. So I'm just going to go shear. So if I were to run this now, we now have a little indicator saying what exactly each one of these is. Now, the last thing that you guys may want to do is just add some axes. So if you guys want to do this, it's simple. It's axis label, so it automatically pops up as the first one. So again, if you want to save some time, you guys can just go tab. And since we want to define two labels, one for x, one for y, we're going to use the squiggle brackets because we're going to do multiple arguments. And it's very simple after that. It's just going to be the x-axis label, comma, the y-axis label. So the x-axis in all these cases is beam length. So I'm just going to go beam length. And then I usually like to put the units. Of course, it's in millimeters. And I'm going to go comma. What is the y-axis? Well, in this case, it is deflection, also in millimeters, just like that. And what I'm going to do is I'm actually going to copy this and just add it to the other graph. So if I was smart, I would have done the axis label originally. Therefore, it would have just kept getting pasted. Nice and easy. For the second function, we're not measuring deflection. We're measuring moment, and it's in units of kilonewton meters. And then finally, for the last one, I'm just going to comma. We're not measuring deflection. In this one, we're measuring shear. And this is going to be in kilonewtons. So if I were to run this now, I have my deflection functions. It says that my deflection's in millimeters. This is the beam length, stuff like that. It's looking pretty sexy. This is something you guys can print, submit, and all your profs will be amazed with your great effort. Now, one thing I want to do before we move on to the stress components is just mention above with Q. Remember that we said it's very obvious or very easy to make a mistake with Q by putting in 50, because that's typically what they'll give you the value as a positive number. However, your ass gets saved a little bit when you plot it, because if I were just to go 50 and run the code, well, then I can see my deflection going upwards, and then I know, hey, something's probably wrong. Oh, it has to do with Q. Switch that back to negative, run it back. We are now good to go. All right, so those are the functions that are functions of x1. Now, when we're dealing with functions of x1 and x2, such as the stress components, it's actually better to use a contour plot. So I'm going to add a thing, and I'm going to go contour plot, which basically shows us the stress distribution over the beam. Now, even though they sound scary, they're actually very, very simple to use. Just like before, we're going to use a very specific command, and instead of plot, it's contour plot. And I just got to make sure I spell it right. So we can see that it actually appears as the second option, so you guys can click it. And just like any other function, we put the square brackets. And contour plot, very similar to just the plot function, except it takes 3 arguments. So I'm going to go comma, comma. First argument, what do you want to plot? Just like the plot function above. Well, let's say we want to plot sigma 1, 1. So I just input sigma 1, 1. The second argument is, all right, what are you plotting it over? Or the first one you want to plot it over. So we know we want to plot it from x1 is equal to 0 all the way to L. Now, the third one is, what is the second axis you want to plot over? Well, we know that we want to plot it from x2 is equal to negative h over 2 to h over 2. And you're saying, hold on, Clayton, why h over 2? Well, remember that when we defined the theory for this beam, we put the axis, the x1 axis, through the centroid of the beam. We didn't put it at the bottom of the beam, we put it at the centroid. Therefore, the height of the beam actually starts from negative h over 2 and goes up to h over 2. Now, if I were to run this and go Shift-Enter, scroll down, I can see that I get this nice plot over here. and it's not so nice in the fact that, again, Mathematica wants to have everything square. So just like the plot function above, I can go comma and add a third, or I guess in this case, a fourth argument. And in this case, I'm going to play with the aspect ratio, and I'm just going to throw it down to 0.25. So I come down here, and now we can see a nice stress distribution over my beam. So of course, this is the beam length down here. And then moving up, we can see the height of the beam. So we specified that our beam was in total 800 millimeters tall. So when we come down here, it checks out because it starts at negative 400 and goes all the way up to 400 over here. All right, and what we can do is we can copy this. I'm just going to take it, copy it, put it down at the next line and say, well, instead of sigma 1,1, let's say I want sigma 1,2. So I just switch that. I'm going to press enter. I come down here. I now have my shear stress distribution. All right, guys, that's it. I'm trying to think of anything, other tricks, tips, anything like that. But no, this is basically it. So, oh, I guess I'll show one more thing. So if we look right here, even though we're given the height of the beam as well as the length of the beam, we don't know the value of the stress component. So something that we can add in other arguments is we can go comma, contour labels. So it doesn't, oh, I guess it's right here, contour labels, and we can set this as true. All right, so what I'm going to do is I'm only going to put it on S11 so you guys can see what it does. Shift enter. And what we can see is we can see the value of the stress components throughout the different contours. And if we have it off, we can't see the value of the stress throughout those contours. So that's it for this little Mathematica example. Again, we solved the exact solution of an Euler-Bernoulli beam, and we found the deflection, moment, shear, as well as the stress components sigma 1,1 and sigma 2,2. So that's it for the example. Thank you guys all so much for listening. I really appreciate it. I will see you guys in the next example.